Okay, so going at this in a completely different direction than the other lectures that we've done, but I thought of, okay, we've got such a short period of time left, and launching into like a regular lecture on the first topics in electrochemistry just feels like a bad idea to me. So what I decided to do instead was sort of wing this overview of electrochemistry to sort of give you a little bit of appreciation for it. When I say wing it, I mean wing it. This is something that I sort of thought of this morning when I woke up about 5:30 and still was uncertain about what I was going to do about this, and so this is where I landed. We're going to start with where we sort of left off last time, which was balancing redox equations. And so we have this particular reaction of silver ion with copper to produce copper plus 2 and silver. And so what I'd like to do is I'd like to go through and I'd like to balance this redox equation with you. We may go fairly quickly through this process just because it's something that hopefully you've practiced or will practice so that you get it down. But we know silver here is a +1. We know copper is a 0. We know copper plus 2 is a +2. And we know silver is a 0. So that's going to help us when we break these apart into half reactions. And our half reactions are going to be silver plus to go to silver, and copper to copper plus 2. And we can start to assign whether these are oxidations or reductions at this point. So we have a +1 going to a 0. All right, so that's getting that the oxidation number is getting smaller, so we'd call that a reduction. It's going from a +1 to a 0. And that would be 1 electron, because the difference between +1 and 0 is 1. So that means that 1 electron must be transferred here. When we have copper to copper plus 2, it's going from a 0 to a +2. It's getting larger. Oxidation number is getting larger. So this is an oxidation process. Starting at 0, ending up at +2. So this is a 2 electron transfer in that half reaction. Now let's go through. Make sure everything's balanced. These ones are nice, remember, because we have no oxygen, we have no hydrogen, we don't have to worry about it. That means the reaction goes probably similarly in basic versus acidic solution, at least theoretically. In reality, there are other chemical reactions that can occur along with these particular ions, so pH does matter. But based on what we've learned, we would see this as a reaction that's neither in basic or acidic solution. It would just be neutral. So let's go ahead and add these electrons in. If we have a reduction is a species that's gaining electrons. So the silver ion must be gaining an electron. The electron is a reactant. All right. And then copper plus 2. The electrons are being given off because it's an oxidation. So the electrons are going to be a product. So copper to copper plus 2 electrons. Okay, great. We don't have to deal with hydrogen or oxygen. Okay, now we got to balance the number of electrons though. Okay, so 2 electrons here, 1 electron there. So we're just going to multiply everything in the silver half reaction to get 2 electrons. So we have 2 Ag plus 2 electrons to produce silver, and copper is left as it is. Cu plus 2 electrons. Whoops, that should be a 2 right there. Now, you might come back up here and look and say, well, this was balanced to begin with. 1 silver here, 1 silver there, 1 copper there, 1 copper there. You would be absolutely right, but it's not balanced in the way that reaction actually is undergone. It's balanced it's not balanced because we've got to take care of the electrons that are being transferred. And in reality, what's actually happening is the sum of those two half reactions. So 2 silver ions plus copper plus 2 electrons, and copper plus 2 silver atoms plus 2 electrons. The electrons cross out, and we're left with 2 Ag ions plus 1 ions plus copper to produce copper plus 2 silver. And that's the appropriate way to balance it. And that's why we have to have this whole different method for balancing a redox expression, because we have to take into account all of those electrons and the electrons that are being transferred. Now I want to think a second, and the place that I really want us to get is I want us to be able to get to a place where we can try to predict whether a reaction like this would occur. If you did something called the activity series in general chemistry at any point, this is going to mirror that conversation. And so I want to sort of teach you why that activity series stuff would have happened in the way that it did. And if you haven't heard of activity series, don't worry about it. It really doesn't matter for the conversation that we're going to have. All right, so I want to come back to this idea. Remember before we would look at things like energy, and we would say this is the progress of some reaction. And we looked at this whenever we were talking about the idea of enthalpy, enthalpy changes. All right, where, we might start with something that has a fairly high energy, and we have a product that's a fairly low energy. All right, and so if this were the case, if this is our reactant, and this is our product, we would anticipate, all right, that the reactant is higher energy, so it would want to react to get rid of that energy and become the product, and that the energy of that particular reaction would be the difference in these two energy levels. And whenever it was heat, we talked about that as delta H. We then moved on to talk about it as if it were free energy. And we said free energy is actually a better way to look at and predict whether reactions are going to occur, because it takes into effect not only the heat, the enthalpy change, but it takes into account the entropy change, how spread out or how dispersed we can make the energy either as in the reactants or as in the products. And so we're going to do the same thing here with redox expressions, where we're going to say, okay, in one of those half reactions, the electrons are fairly high energy. And in one of those half reactions, the electrons are fairly low energy. And so if we want to try to predict whether a redox reaction would occur, if we could look at the difference in energy between those two of the electrons in those two half reactions, we could then in a fairly straightforward way predict whether a reaction would occur. All right. So, what we're going to do is we're going to look at the potential energy of electrons. And we're going to plot that versus some reaction progress. Oh boy, you all are getting your money's worth today, and I'm sorry my writing is terrible. It's probably a little bit worse because I'm going off the top of my head. Now in our example, we had silver, right? So we had 2 Ag plus copper goes to 2 silver ions plus copper plus 2. All right, and we had the two half reactions. We said 2 Ag plus 2 electrons produce 2 silver atoms. That was one of our half reactions, and the second was copper goes to copper plus 2 electrons. And so what I'm going to do is I'm going to tell you that, I know enough about this reaction to know in which of these half reactions do the electrons have more energy. Okay? And it turns out that the electrons in the copper, okay, are higher energy than the electrons in the silver reaction. Okay, and I know before we had sort of looked at, products versus reactants, and we had tried to predict the difference between them, but now we're looking at the electrons in that half reaction, no matter whether they're in the product or whether they're in the reactant side. And we're looking at the energy of the electrons, no matter whether they're in the product or the reactant side. And you might say, but that's a chemical reaction. How can they be the same energy on both sides of that reaction arrow? And remember, it's not a full chemical reaction. It's a half reaction. You have to have two half reactions to make a chemical reaction or redox reaction go. All right, you can't just do one without the other. And so when we look at the energy, we're looking at the energy of the electrons on both sides. If we have a piece of copper, it's not spontaneously just going to start giving off electrons. And if I have silver ions around, it's not going to spontaneously just start taking in electrons to produce silver. I mean, something's got to force that along. If you've got an oxidation, you've got to have a reduction. So if we look at this, as we've drawn it, okay, those two electrons from that copper, okay, they're going to want to get to a state where they're lower energy. So if there's some silver ion around and there's some copper around, these two electrons are going to hop down to that lower energy level. And we're going to end up with two electrons that have come into this system. Where do those two electrons go? Well, they're going to go to the most electron-poor species, the one that has fewer electrons, the cation. All right? So those two electrons are going to go with the cation to produce silver. And here, the two electrons are leaving, they're being given up. Where are they going to be given from? The one species that has the most electrons, which is the copper atom. It's right here. It's got more electrons than copper plus 2. Copper plus 2 has already lost 2 electrons. So the copper is going to give up 2 electrons. Those 2 electrons are going to go to the silver ion to produce silver and copper plus 2, which is exactly what we know from the balanced chemical equation. All right? Now, the thing about it is, how did I know that this one's more, that this one is more higher energy than this one? And it turns out that we can measure the energy of the electron in a half reaction. And when we measure that potential energy, we call it an electrode potential or a standard reduction potential. That's probably a better term for it, is a standard reduction potential. And if you look here, here's a chart of standard reduction potentials. It's going to give us what we're going to call the E0, the potential of the half cell, all right, of the half reaction, in a unit that we're going to term as volts. We're going to think of volts as an energy unit. At this point, that's all the more I really want you to get out of it, is that it's essentially an energy unit. And so, this tells us the energy of those different electrons in those different half reactions. And you'll notice these are all half reactions, and on the right here we've got their potential energies. But I'm going to tell you that this chart is a little bit backward. And what I mean by a little bit backward is that I'm going to come back to our little chart here, okay, where we have potential energy of electrons. And I'm going to tell you that the axis here, normally we'd think of positive at the top and negative at the bottom. But in reality, the way that this system has been developed or devised, negative potential energies are higher energies. Positive potential energies are lower energies. So if we come back, all right, to our chart of standard reduction potentials, and we look at silver, all right, silver plus electron to produce silver, okay, you might say, oh, but our half reaction was 2 silver ion plus 2 electron to produce 2 silver, and I'm going to tell you that the stoichiometry of this reaction really has nothing to do with what the stability or the energy of the electrons would be in that half reaction. So we don't care so much about the stoichiometry when we're comparing this, all right? And I want you to notice here that the potential is 0.80 volts. Now I want you to look at copper. Copper plus 2 electrons to produce copper. All right, and you might say, okay, but that's backward from what we saw before. And in reality, it does not matter. The energy of the electrons doesn't matter, in that half reaction. Doesn't matter which way we write it, whether it's flipped or whether it's the right way. It doesn't matter about the stoichiometry. And I'm going to tell you, this is really the point where I'm going to deviate significantly from what you've learned before about electrochemistry, because almost everyone teaches electrochemistry wrong. I didn't realize it till I got to graduate school, and I had a course on electrochemistry, and I just absolutely loved electrochemistry. I didn't realize how much I loved redox. It's funny that I've been doing redox stuff for about the past week for you all, and going around and just telling my wife, I'm like, this is my favorite thing to teach. I think of anything that I teach, I just love teaching redox. And maybe that explains why I'm an electrochemist. But you would have learned that, okay, if you switch the reaction around, the sign of the energy, the potential changes, and none of that stuff is real. Okay. The energy of the electrons in this half reaction is the same no matter which way you write it. Okay, if it were not, then this reaction would happen spontaneously without another half reaction, and that's not the case. All right, so it doesn't matter which way you write this. That's the energy of the electrons in that half reaction. It doesn't matter how we write this or whether there's a stoichiometric coefficient multiplied through by this equation. That's the energy of the electrons in this half reaction. And that's an important thing to take away. So let's come back to our chart and think about this for a second. So we said, okay, copper is plus 0.34 volts. And we said silver is plus 0.80 volts of energy. All right. Now you might say, okay, how do I know whether this reaction, how do I know that that reaction occurs this way? How would I know that I might predict that this is spontaneous? All right, that this reaction is likely to occur. Now I hate to say spontaneous because, we know that we really need to know the enthalpy, we need to know the entropy change, all those things, and we don't have that information here, but we're going to be able to get to that same information here in a second. All right, so yeah, when we look at this and we're thinking about potential energy of those electrons, we can predict spontaneity without having to go through all that other work of entropy changes and enthalpy changes. And to do that, we're going to find the change in potential. Now, this is another difference. A lot of times you'll see this just written as an E. It's always a change in potential energy. All right? And I'm going to tell you that the way that we define this is the potential of the reduction process minus the potential of the oxidation process. That is not the way that your textbook will teach it. That is probably not the way that you learned it before, but this is the right way to do it. I can tell you that as an electrochemist of, 20-some years. All right? This is the correct way to think about it. And so let's go ahead and determine what the difference in potential energy is between these two half reactions. So we need to know which one we're treating as the reduction process. And the reduction process we're treating as the silver, right? It's being reduced. So that's plus 0.80 volts. And I'm going to subtract from that the reduction potential, the electron energy, potential energy of the oxidation process, the copper, minus a plus 0.34 volts. And our change in potential energy for that particular reaction, I'm going to plug it into the calculator just to make sure I get it right. So 0.8 minus 0.34 is plus 0.46 volts. All right, so we can predict what the sign and the magnitude of the energy difference would be between the reactants and the products in any redox reaction. Okay, now the payoff of all of this is that we know when we have this reaction written in this way, that we know that change in potential energy is going to be equal to plus 0.46 volts. All right. And now I'm going to tell you that this change in potential energy between those two half reactions is related to free energy. So the free energy change is equal to minus N times F times delta E. Sorry, I wrote that terribly, so I'm going to rewrite it. Okay, I'm going to actually cross it out because I'm unhappy with how I wrote it. Minus N times F times delta E. I'm going to put it in parentheses so you can see it very clearly. N, number of electrons that are being transferred in that redox reaction. We know already from balancing this that this is a 2-electron transfer process. Because when we added those two reactions together, each half reaction had 2 electrons in it. So N is 2 electrons. F is the Faraday constant. And I'm going to tell you off the top of my head, I can't remember, 96,487, I think. But it is essentially the charge of a mole of electrons, all right, in coulombs. All right, and then we've got our potential. But the reason I show you this isn't because I want you to plug anything into this equation. In fact, I'll be a little disappointed if all you do is try to plug into that equation and get something. In fact, I'm not going to do an example of that. But what I want you to think about is, what is the sign of delta G if we have two constants, and those two constants are both positive? So positive, positive. And then we've got our change in potential. Our change in potential here, okay, in this case is positive, right? So we're going to have 3 positives multiplied next to one another with a -1 out in front. So what's the sign of the free energy change when all 3 of those things are positive? Yeah, it's going to be negative. And if delta G is negative, spontaneous. All right? So that potential energy difference between those two half reactions is going to tell us about the spontaneity of that reaction. All right? Now, I'm just going to take this reaction and flip it around. Let's say instead we took a piece of silver and we put it into a solution of copper plus 2 ions. All right, and you might say, I never really thought about it like that. But if you look at this reaction, essentially it's saying that if we take a piece of copper and we put it into a solution of silver plus 1 ion, we're going to get this reaction to occur. So we're going to get silver metal to form, and we're going to get copper plus 2 ion to form. Now we're saying, okay, we're going to take a piece of silver and put it into the copper solution. Now my question for you is, will this reaction occur in the same way that that one will? We said that's spontaneous, so that should happen. All right, so if we put that copper in that solution of silver plus 1 ion, we should see some silver form, and indeed that does happen. Okay? So will this one happen? Well, our chart, remember our chart would be backward. Now this would be our reactant, and that would be our product. So the electrons would have to go uphill energy-wise, would have to go uphill energy-wise in order to get, in order for that reaction to occur. If we were calculating the change in potential energy of the electrons between those two half reactions, it would work out to be negative 0.46 volts. Because when we write this, now the silver is being oxidized and the copper is being reduced. So whenever we go through and we say delta E is equal to E reduction minus E oxidation, potential of reduction minus potential of oxidation, those two things are going to be backward from where they were before, and our change in potential is going to be negative. Now when we try to calculate delta G equals minus N times the Faraday constant times the potential difference, now we're going to have a positive and a positive and a negative. So negative 1 times two positives would be negative, times a negative is positive. Now delta G is positive. We would predict that's non-spontaneous. So that redox reaction wouldn't happen. Okay? You know, there's a lot more to be said about electrochemistry, but you know, I'm not going to jam a whole bunch of material at you at the very end of this class, especially because we're not in the classroom. I wouldn't do it in the classroom. I'm not going to do it here. And so this is it. This is the last bit of information. You know, I want you to understand redox reactions. I want you to be able to try to predict whether a redox reaction would be spontaneous or not using these tables of standard reduction potentials. All right? I want you to understand what that means physically. Could you draw that diagram like I drew to support your prediction? Those are the types of things that I would want you to be able to do from this. Okay? And that's sort of the end of the last lecture that I'm going to give you for the semester. I probably will have a closing note at some point before we get done. You know, the fact that we had to run the class in this way means that your class, probably more so than any class that I've ever had, is going to stick in my head because this experience was so different. And I just want to be able to convey a little bit of that thinking to you before we go. But that'll be something that, you know, when you go to turn in your final exam, you'll be able to watch it and see. And I'll be anxious to hear back from you about the experience as well. Okay, so that's it. Have a great day, everyone.